Well, welcome back to the Calhoun Marine Engineers Beneficial Association Engineering School here in Easton, Maryland. And we're here today to talk about shipboard grounding practices and shipboard ground fault detection. We'll be using our ground fault detection trainer, and we'll be explaining the circuit on the board. So first off, let's talk about the ground fault detection trainer. Well, what we have here, we have 3 bus bars that represent phase A, B, and C on our distribution system. We have another bus bar that we're going to call ground or hull, and we have 2 sets of lights. The first set will connect in Y across the 3 phases, simulating a load connected in Y, and we have another 3 lights which we will be connecting in delta to simulate a load connected in delta across our 3-phase distribution system. And finally, we get to our ground fault detection box. It's an ingenious circuit. It's very simple, and it works excellently with detecting resistance faults. So let's talk about what we have inside the detection system. As you can see, we have 1, 2, 3 indicator lights connected in a Y fashion, and the center of the Y is connected to the outside of the box via a push to test normally closed push button. And so let's go ahead and make the connections, turn on the power, and see what happens. Okay. So I have 208 3-phase coming out of the wall. Come back to some transformers we have back here that give us our 3-phase 120 that I'll now hook up to the bus bars. Okay, we have 3-phase AC. Now, the first set of lights here, we said we're going to connect in Y, so we'll take one end of the bulb and we'll hook it up to phase A, phase B, and phase C, and we'll take the other side of the bulbs and connect them all together to form the center of the star. I've insulated the back end here. We'll drop it over for safety, get it out of the way. Now the other set of bulbs we said we were going to connect in delta. So to connect in delta, one end of the light will go to one phase and the other end to a different phase. So first one I'll connect between phase A and phase B. Second one I'll connect between phase B and phase C, and thirdly we'll connect between phase C and phase A. Okay, now our ground fault detection system gets connected, well, one light gets connected to phase A, the second light will connect to phase B, and the third phase will connect to phase C. The third light will connect to phase C. And the last connection we make is the one from the center of the Y via the normally closed push to test push button to the ground or to the hull. On our shipboard installations, this is the only normal connection between the electrical system and the hull. This is the only one that's supposed to be there. Okay, we'll turn on the power and see what happens. Well, as expected, the bulbs connected in Y are not burning as brightly as the bulbs connected in delta. These bulbs are seeing 69 volts between their phase and the center of the star. The bulbs in delta are seeing 120 volts between the 2 phases they're connected between. Our ground fault detection system, as we do not have a ground fault now, all 3 bulbs are burning at equal brilliance and dimly. Okay, so now let's say what happens if we develop a ground fault. We have a jumper here that we can connect between one of the phases and the ground to simulate a resistance or a low resistance fault to ground. So I'll connect this jumper between phase C and the hull. As you can see, the indicator lights now change dramatically. The light for phase C has gone out, and the lights on phase A and B are now burning brightly. We use our push to test button, which will disconnect the center of the Y of the indicator lights from the ground, and we'll see that the bulbs return to their normal condition, indicating that our detector is working correctly. So let's go to the board, make the hookups, and see what happened. See if we can explain what happened. Well, we said we connected our detector box in between phase A and one of the indicator lights, between phase B and the second light, between phase C and the third light, and our final connection went from the center of the Y to the hull. We then added a ground fault. We connected our ground fault from phase C to the hull. Well, I often find it useful to redraw a circuit to aid in better understanding. So wouldn't it be fair if instead of showing that fault like that, if I erased all this here and showed now that I have taken the center of the Y and I brought it to the same potential as phase C? Sure, that's essentially what happened. The only thing we haven't done is we've taken out the normally closed push to test button, but essentially that's what we've done. So it makes good sense why the bulb on phase C has gone out, because there is no longer any potential difference across the bulb at phase C. One side of it is connected to phase C, and now that that neutral point has been brought to the same potential as phase C, there is effectively no potential across it. Similarly, the bulbs for phase B and phase A, they have now been connected not between their phase and a floating neutral, they're now connected between phase B and phase C, and phase A and phase C. So instead of seeing phase to neutral voltage of 69 volts in our 120 volt distribution system, now they're seeing the full 120 phase to phase voltage. Well, I hope you enjoyed our presentation. I hope you've learned something. Thanks a lot.